Hydrocarbons are known to be non-polar and they are organic compounds, meaning that no matter how many carbons they are, one, two, three carbons, whatever, all hydrocarbons, whether they are alkenes, or alkynes, these they behave like oil. So when you want to mix them with water, they are insoluble in water, and they form two separate layers in there. Now, always the hydrocarbon layer is lighter, and the water layer, which is the aqueous layer, that water layer is going to be the denser. So the water layer is going to be at the bottom, the organic layer is going to be at the top. Please remember that with alkanes that are less than 5 carbons, these are gases. And more than 5 carbons, these are liquids. Alkenes and alkynes, they are all liquids in there. And all of those are water insoluble. Now, with respect to the types of alkenes, when we start reactions with alkenes, it's very important to know what type of alkene you are working with. And in order to know what type of alkene you are working with, all what you need to do is simply check the double bond. So what we do is we locate where the double bond is, and then we see how many carbons are there on the double bond. So on this double bond, I normally divide it in half like this. And then on this carbon of the double bond, this carbon is connected to one carbon. Okay, because you do have your double bond, and we know that the double bond has a carbon. So the double bond has 2 carbons in there. On this carbon, I have no carbons connected, but on this carbon, I have just 1 carbon. So I'm going to call this a mono substituted alkene, because it only has 1 carbon in there, so it has 1 substituent, so it's called a monosubstituted alkene. For this example over here, again, you highlight the double bond and then see how many carbons are there around the carbons of the double bond. So these are the carbons of the double bond. I want to see how many carbons are there around the carbons of the double bond. So I do have a carbon here and a carbon there. These are 2 R groups, 2 substituents. So this is why I'm going to call this a di-substituted alkene. And this di-substituted alkene, notice that the 2 CH3s, they are opposite with respect to each other. So this di-substituted alkene is a trans. This one over here is again a di-substituted alkene, because you do have 2 carbons in there. So this one is going to be a di-substituted alkene, but it is the substituents are on the same side. Substituted alkene, but the substituents are on the same side, so we're going to call this trans. So when we talk about di-substituted alkenes can either be cis or trans. And then we have this example over here, where if you highlight the double bond and then just cut that double bond in half, so that you would see every carbon of the double bond, how many carbons it's connected to. So on this part, or on this carbon, I mean, you have 2 carbons connected to it, and on the other one, which is on this carbon, you have 1 carbon connected to it. So in this case, you have a total of 3 carbons around the double bond. So we're going to call this a tri-substituted alkene. So this one is going to be a tri-substituted alkene. And then the last thing is this system over here, where you have a double bond and you have 4 R groups around the double bond. And this is called a tetra substitute. Tetra stands for 4. So you have 4 alkene groups, so that is going to be a tetra substituted alkene. Okay, so you have a monosubstituted, a di, substituted, a tri-substituted, and a tetra-substituted alkene. Let's have, for example, an example here. Let's say if I have something like this, if I have a cycle, if I have a double bond, and if I have a CH3 in there, and I ask you, what type of alkene is this? Is it a mono, di, or tri, or tetra substituted alkene? So you do exactly as I did. You go ahead and you highlight the double bond in there and see how many carbons are there around the carbons of the double bond. And here I have one carbon, I have one here, and I have one there. So that is going to be a tri-substituted alkene. Okay. Another example, something like, for example, something like this over here. So if I have something like that, if I have a double bond, here you go. So if I have a structure like this, and again, I ask you, what is the degree of substitution or what type of alkene is that? Then you would need to highlight the double bond in there and see how many carbons you have around the double bond. So here I have one carbon, I have one carbon, and I have one carbon over here. 3 carbons around the double bond. So this is called a tri, again, substituted alkene. So it's very simple. Locate your double bond and see how many carbons are connected to the double bond, and this is how you know the degree of substitution of your alkene. Now for the reactions of the alkene. Alkenes are made up of double bond, and whenever you want to do a reaction, the reaction is called an addition reaction, meaning that you are adding to the double bond. Now when you add the double bond, you end up breaking the pi bond of the alkene, because here the alkene, we know that it's made up of a sigma and a pi. So for the reaction to happen, the pi bond will be broken, and then I will be adding. This is why I call it an addition reaction, because I will be adding the reagent to the double bond. The reaction starts by simply having an alkene, and that alkene reacts with a reagent. The reagent, normally this is a general reaction. The reagent is AB. We'll give specific reactions as we go, but this is the general format of the reaction. You will have a solvent, and the role of the solvent always is to allow the reagent to dissolve with the alkene. Both the alkene and the reagent, these are called, both of them, these are called reactants. So both of these are called reactants. Okay? Both of them. So I am starting with my reactants. I am using a solvent to dissolve those two reactants together. This is why the role of the solvent is very important, but the solvent isn't just to dissolve the reactants together. The solvent will not show in the product, so I'm not going to see the solvent in the product. What I'm going to see is that reagent being added to the alkene. This is what I'm going to see. With these types of reaction, the functional group is the alkene. This is the reactive part of the molecule. So the pi bond is going to break, and I am going to add one part of the reagent to one carbon of the alkene, and the other part of the reagent to the other carbon of the alkene. So as you can see in the product, I am breaking the pi bond. So this pi bond, I will be breaking it, and I'm going to be forming 2 new sigma bonds in here. I'm going to be forming 2 new sigma bonds in there, and those sigma bonds are between the carbon in A and the carbon of B. And this is called an addition reaction. This is called an addition reaction there, where a sigma bond is where a pi bond is broken and 2 sigma bonds are formed. Let's be specific now. There are 4 reactions that we will go over. The first one is the reaction of hydrogen halide. The halogen can be either chlorine, bromine, or iodine. So we're going to again start with the starting material in there and with the HCl or HBr or H iodine or H iodide. It doesn't matter, any one of those. The solvent here, I am using CCl4, which is named as carbon tetrachloride. So carbon tetrachloride. The role of the solvent is to allow the HCl to dissolve with the alkene. Remember what we said, that alkenes are water insoluble. HCl is water soluble. So if I want to dissolve both of these together, they won't dissolve. They're going to form two separate layers. This is why I need a solvent in here to allow these two reagents to mix with each other, to allow the starting material and the reagent to mix with each other. Okay? So how does the reaction happen in here? The reaction normally goes under what we know, a rule, and the rule says that this is an addition reaction. It is a scientist whose name is Markov-Nikov, which says that hydrogen, when hydrogen adds to the carbons of the double bond, because we know that the addition is around the carbon double bond carbon. Okay. However, if you take a look at the type of the double bond that you have at the alkene, this is an alkene that has its carbons not the same. This is why we say it's an unsymmetrical alkene. This carbon is a CH2, while as this carbon is connected to a cycle. So these two carbons are not the same. We say that this is an unsymmetrical alkene. So when we have an unsymmetrical alkene and we want to add the H and the Cl, where should the H go? Where should the Cl go? Because I know that the addition is on these two carbons, but where should they go? So the rule says that hydrogen normally adds to the less substituted carbon, and the halogen, I'm just going to add it as an X because the halogen can be chlorine, bromine, or iodine. So we're going to be general in this case. The halogen is going to add to the most substituted carbon. Okay? This is actually the rule in there. So we're going to start always by adding the hydrogen. But before adding the hydrogen, we want to see which one of these carbons is the most substituted and which one is the least substituted. Well, you can take a look and see that this carbon 1, this is carbon number 2. I am simply, you can number it. I am not numbering it for naming it, but if you want to number it the right way, this is going to be carbon 1 and carbon 2. So carbon number 1 is connected to a carbon here. Okay, so I would say that carbon number 1 is more substituted, and carbon number 2 is not connected to any carbons. It has two hydrogens on it. So carbon number 2 is going to be the less substituted carbon. So now I know that whenever I want to add a hydrogen, hydrogen will come and add to the second carbon, carbon number 2. So this is how the reaction happens. The reaction happens in steps, and I will be forming an intermediate. Intermediate is actually not the product. Intermediate is what comes before the product. So in order to represent the intermediate, I'm just going to go ahead and open these brackets in there so that I would put the intermediate. And the intermediate is actually your reactant, okay? So it's actually your starting material. And I do have here 2 carbons. But now what I'm going to do is I'm going to apply the first step of the Markov-Nikov. Hydrogen adds to the less substituted carbon. So I'm going to add the hydrogen here. Now, the moment I add the hydrogen on this carbon, because it is a less substituted carbon, so this is the addition of the hydrogen in there. Remember that I do have 2 hydrogens here. Okay, let's use another color in there. So these are the actual 2 hydrogens, and the hydrogen that I am adding is actually this over here. So I am adding this hydrogen to the less substituted carbon. The other carbon will end up being a positive charge in there. And that positive charge, we call it an intermediate carbocation. So this is an intermediate carbocation. We represent the carbocation by a C plus. So you can just say intermediate C plus in there. This is the intermediate before I reach my final product. What is my final product? That halogen here, that X, is gonna come and attack the plus charge. So the final product in this case, I'm just gonna write it like this. The final product is the X. Our X here is the chlorine. So that Cl, it's gonna be a Cl minus, by the way, because you allowed the hydrogen to leave, so that chlorine will be negative. And negative and positive, they do attract each other. These have opposite charges, so they are going to attract each other there. So the Cl is going to come and attack the positive charge, the carbocation in there, and your final product is going to look like this. Your final product in here is going to have the chlorine on this carbon, and already I've added the hydrogen here. So it's as if this is what's happening in there. I broke the pi bond. So I started with an alkene. My product has no longer an alkene. Between carbons, let's have the same numbering in there, between carbons 1 and 2. So between carbons 1 and 2, no longer I have an alkene in there. And then I applied Markovnikov. Hydrogen adds to the less substituted carbon, and the halogen adds to the most substituted carbon. You are responsible to know how to draw the intermediate of the reaction. Okay, since I am using a reagent and a solvent, there are multiple ways in order to represent this reaction. I can have the reagent and the solvent above the arrow, so I can represent them like this over here. Instead of having the HCl on this side of the arrow, I can have the reagent on top. This is the reagent on top of the arrow, and on the bottom here, that's going to be a solvent. Notice that the solvent has no role in here, so you don't see it. Why you don't see it? Because your product is supposed to be dissolved in the solvent at the end. So you don't see it in there. It has no role. You're not adding anything from the solvent. The solvent is just making sure that HCl and the alkene, they mix with respect to they mix with each other. Or I can, instead of showing the reagent on top, the carbon tetrachloride under the arrow, I can put them next to each other above the arrow in there, and all of these representations are right. So I can represent the reaction by this way, or I can simply represent it this way. So please get used to this type of representation. Okay, let's have another example. In there, and with those, again, it's important that you know what type of degree of substitution you have in your structure there. So let's see. So what you have over here is a simple alkene, and you're reacting HBr with it. So this is going to be my alkene. I always would like to highlight my alkene in here. This is a tri-substituted alkene, but since I am adding on that double bond, because this is my functional group, and functional group are the reactive part of the molecule, so I'm expecting any addition to be on that double bond. Then hydrogen and the bromine will follow Markovnikov and will add to the less substituted and the most substituted. So to locate the less and the most substituted over here, simply you do have this carbon there. So let's say this carbon over here and this carbon over here. These are the carbons that we care about, that the addition will be on. So this carbon is going to be the less substituted, Why it's the less substituted? This carbon is connected to one carbon, while as this carbon is connected to two carbons. So this one is going to be the most substituted. It's enough to label which one is the least, which one is the most, to know where the hydrogen is going to add. Because the first step, hydrogen will add, and the second carbon will be a plus a charge. So now my hydrogen is going to add over here. So I'm going to use another color in there, and that is for the hydrogen in here. I already had my my hydrogen there that was in the structure. Okay, I've just wrote it, and my plus a charge now is going to be on the adjacent carbon, so that is going to be the plus a charge in here. Your addition is between those two carbons because this is where the double bond was. Okay, but in your product you should not see any trace of the double bond because you are breaking the pi bond and you will be forming two sigma bonds. You formed one here. Now with the Br minus, that Br is going to come and attack that plus a charge, and then your product in this case is going to be, here you go, I'm going to end up adding this hydrogen here and the bromine over there. Okay, and again, this is where the double bond was. You don't have to write the hydrogen because we're expressing it in a skeletal form, but I'm just showing you in there that we are adding the hydrogen and the bromine. You are responsible to draw the intermediate of the reaction, the intermediate carbocation of the reaction though. This is another example. Now, Markovnikov, we do apply it whenever the alkene is not symmetrical. This means that the carbons are different of the alkene. But if the carbons are the same of the alkene, notice here this alkene has carbons that are the same because the hydrogens on the alkenes are the same and the carbons here on the alkene are the same. So we say that this is an example of a symmetrical alkene where the R groups on the alkenes are the same. That's going to make those two the same, so it really doesn't matter where the hydrogen go and where the iodine go. Just pick one. So my product, if I pick the hydrogen to go over here, this is my pi bond, then when I draw my product, I want to make sure to break that pi bond. I am going to add, keep those hydrogens in here. I still have them. So I'm going to add this hydrogen. I'm going to add it here. Then the second carbon will be a positive charge. And then I would have my iodine added in there at the end. So my iodine in there, it's going to be on the positive charge carbon to end up having formed two sigma bonds. So I have a hydrogen there. This is going to be my final product where I would have added a hydrogen and an iodine. Okay, let's write the iodine right. This is the hydrogen and that is the iodine in there. So no need to follow Markovnikov whenever you are working with symmetrical alkenes.